Okay, so this is the next video in our series reviewing and supplementing Chapter 5 of your textbook, which is discussing short-term and working memory. So in this particular video, we're going to talk more about short-term memory. So far we have introduced the modal model, and we've also talked extensively about sensory memory. So now we're going to turn our attention to the next structural feature of the modal model, which is short-term memory. Okay, so the most complete definition of what short-term memory is as follows. So short-term memory is defined as the capacity for holding but not manipulating, okay? Holding, not manipulating, and that's going to be an important distinction for when we start to talk about working memory in my next video. But okay, so short-term memory is the capacity for holding but not manipulating a small amount of information in the mind in an active and readily available state for a short period of time, right? So as far as the active and readily available state, that is reminiscent of one of the features of the modal model that we talked about. So remember when Rachel was ready to order pizza again, and she retrieved the memory of the phone number from her long-term memory, and it entered her conscious awareness, which moved it to short-term memory, right? So short-term memory essentially holds information in mind in a way that allows you to capture that information or hold that information in your conscious awareness, okay? So the only reason I have the picture of William James up here is because he wrote extensively about what he called primary memory or immediate memory. So yeah, so let's go ahead and get started with short-term memory. Okay, so again, the function of short-term memory is going to be that it allows for recoding of information from sensory memory into longer storage. Okay, so some of the information in short-term memory goes into long-term memory, which means it gets stored for an indefinite amount of time. And rehearsal is going to be a really, really important part of short-term memory. So according to Atkinson and Schifrin, when they first proposed the modal model, maintenance rehearsal, or saying it aloud to yourself, or saying it to yourself over and over again, is going to maintain, that's why it's called maintenance rehearsal, a memory trace for a short period of time. And they alleged, Atkinson and Schifrin alleged, that rehearsal also helps to transfer information from short-term memory to long-term memory. Now we know that maintenance rehearsal is not sufficient, so if you want to remember something, you should elaborate on it, right? Or relate it to something that currently resides in your long-term memory, which is called elaborative rehearsal. But both types of rehearsal, maintenance and elaborative rehearsal, are going to be really important to this short-term memory feature of the modal model. Okay, so just like we had George Sperling, who was studying or trying to determine the capacity of sensory memory, we have George Miller, who was interested in determining the capacity of short-term memory. And he proposed that we can hold about 7 plus or minus 2 chunks, which are meaningful units of information that have been recoded from sensory input. Okay, so what are chunks or units of information? Well, it depends upon the type of information you're talking about. Words are considered chunks of letters or units of information constructed from letters. Multi-digit numbers are chunks of single-digit numbers. Routes are chunks of locations, right? So it just depends upon the pool of information that you're using and how you have decided to recode or distribute that information. Okay, so again, one of the things that George Miller was really invested in doing in his research was determining the capacity of short-term memory, and he found that while the average capacity was 7 plus or minus 2, which corresponds to between 5 and 9 units of information, they did vary somewhat depending upon the type of information you were talking about. So if we were dealing with numbers, it was around 7.7 on average. Letter span was about 6.35. Word span about 5.5. And trigrams, which are basically what Ebbinghaus used in his experiments. So just 3-letter words or stimuli. That's about 3.2. However, more recent measures of short-term memory capacity have set the unit, or the limit, the capacity, much smaller than Sperling's. So Sperling said that we're capable of remembering between 5 to 9 units of information, and the average, when he did his measures of span, were mostly around 7 items or so. But it turns out that more recent research suggests that the capacity is much smaller. So these were based on what are called change detection experiments. So in these particular experiments, a participant would see an array of shapes for about 100 milliseconds, and then they would see a blank screen, and then they would see a different screen, and they would be asked to indicate whether that display is the same or different as compared to the first display that they saw, right? So you might notice right away for A, the example A there, that they are different because the square in the bottom left corner is black in the first display and it's green in the second display, right? So that was a fairly simple task, but it gets infinitely harder as you add more items. So there are 3 items in the example A that you see, but there are 8 items in the second example in B, and it becomes a much harder task. And so the reason why we now estimate the short-term memory capacity to be around 4 items is because in this particular experiment, they found that people's performance or their accuracy in this task, so their ability to say correctly whether there has been a change or not, starts to decline rapidly as the number of squares increases, or the number of, so as the number of items increases beyond 4, performance declines rapidly, right? So what that suggests is that people are having a lot of difficulty holding more than 4 items in mind at once. But in any case, regardless of what your initial capacity is, you can increase your short-term memory capacity if you improve your ability to chunk things, right? And when we chunk things in a way that allows us to integrate and elaborate our knowledge of those new units of information with information that already resides in our long-term memory, our short-term memory capacity is going to improve even more, right? So I'm going to show you several examples of cases where you can increase your short-term memory capacity by engaging in this meaningful or elaborative chunking strategy. So this is an example of a case study. So these particular researchers worked with an individual who was only identified by his initials, which were SF. And so they worked with this individual for 2 years, and they did a total of 321 hour training sessions. And in that period of time, his digit span, or the number of numbers that he was able to hold in his short-term memory, increased from 7 items to 79 items, right? So that's almost 11, or a little bit over 11 times more numbers than he was able to retain in his short-term memory initially, right? So how did SF learn how to engage in this meaningful chunking strategy? Well, he was a member of various track and cross-country teams in high school. So one of the ways that he would engage in this chunking strategy is to imagine the numbers as running times, right? So I made a 4-minute and 13.1 second mile time is how he would remember 4131. But he also used other strategies. So for example, he would remember the sequence 1943 as near the end of World War II. Okay. So again, what is at the heart of this chunking strategy is that idea of integration and elaboration. So taking new information that is virtually meaningless to you, or random, totally random, and attaching meaning to it, or basically allowing for it to become associated with information that is meaningful to you. Interestingly, while his digit span increased dramatically, or his the amount of numbers that he could hold in his short-term memory increased dramatically, his memory span, or memory capacity for letters and words, remained the same as they would be for anyone else, right? So it's specific to engaging in this chunking strategy, is specific to what other sorts of information you're trying to learn. Okay, another example, this is a really famous study looking at chess experts or chess masters as compared to novices. So hopefully you guys have already watched the video showing how chess experts are able to do this, or showing some of that experimental footage. But essentially in this study, they looked at the memory for chessboard positions among novices who had fewer than 100 hours of experience playing chess, and experts who had over 10,000 hours experience playing chess. So they placed up to 24 pieces on the board, and players viewed them for 5 seconds, and then were asked to reproduce the positions of the pieces from memory. Okay? And in one case, the pieces that they viewed were from an actual game of chess, right? So all of the pieces were arranged in a meaningful way that was consistent with the game positions that you would see in an actual game of chess. Okay? So there are two examples of chess pieces that can be chunked or meaningfully grouped based on actual game positions. So the chess masters or the chess experts, their memory for actual chess game was significantly better than that of novices or beginners when they were actual game positions, right? Because they could engage in this meaningful chunking strategy based on information that already resided in their long-term memory, right? Because they already knew how to arrange these chess pieces in meaningful positions, rather than having to remember where individual chess pieces were located, they could simply remember, okay, they were arranged in this position. The 4 or 5 pieces that I saw were arranged in this position and this position. So it's really 2 or 3 units of information if you try to remember them by position, as opposed to trying to remember the position of each of those individual 24 pieces, which would be much more difficult. However, they also had a condition where they just showed a chessboard with random pieces strewn kind of everywhere, right? So this would have been a case where even the chess experts weren't able to engage in that meaningful chunking strategy, right? Because the position didn't correspond to anything relevant to the game of chess or anything that would have been meaningful to them. So in that case, there was no advantage for the chess experts because they can't engage in that meaningful chunking strategy. So the performance among masters and beginners, or experts and novices, was exactly the same. Okay, so that concludes our discussion of the capacity of short-term memory and how it can be increased by engaging in that chunking strategy. Now let's talk about how information is represented in short-term memory. Okay? So remember, encoding is just the process of getting something into memory, right? So how is information represented when it gets encoded into short-term memory, right? Well, there are 3 possibilities. We can talk about information as being auditory, which means it's coded based on sound properties or linguistic properties. We can also talk about something as having semantic coding, which means it's coded based on meaning. And lastly, we can talk about visual coding, which means something is represented based on its visual properties. Okay? When it comes to short-term memory, there is a lot of evidence to suggest that information that gets encoded in short-term memory is represented auditorially or based on sound properties. Okay, so I'm going to show you a couple different examples of experiments that seem to very convincingly suggest that information is represented in short-term memory based on sound. So one of the classic examples was conducted by Conrad in 1964. And in this particular experiment, they showed participants some letters very, very briefly, and then they asked them to write down the letters that they remembered. And they included letters that either looked similar, So like V and X have a kind of similar structure to them, or letters that sound the same, like V and C. And then they asked people to write down what letters they remembered. And when they looked at the common errors that people made, so what happened, what letters people tended to write down that were incorrect, they found that people tended to confuse letters with similar sounds, right? So they tended to, if they saw a V, they tended to say C instead rather than X, which looks the same, right? So that's one example that suggests that short-term memory is coded acoustically or based on sound. Okay. Another example, similar idea, participants learned lists of words, and in all the lists, the words either sounded alike or had similar meanings or were unrelated. So they either saw cat, hat, that is said twice, cat, hat, mat, right? Or tiny, small, and little would be words that were synonyms for each other, or they were just unrelated words. And what they found is that there were more subsequent errors, or short-term memory performance was worse when participants studied lists of words that sounded alike than when they studied words that had similar meanings, right? So you can see there that semantic were words that were synonyms of each other. The control groups were words that were unrelated to each other. And the phonological group were words that sounded the same. And people made more errors when the words all sounded the same. Okay, one more experiment. In this experiment, they presented two different types of materials to native Chinese speakers. So they presented either Chinese radicals, which are stimuli that have no sound associated with them, or they presented Chinese characters, which do have sound-based properties. And what they found is that people recalled more Chinese characters than the radicals, right? So what that suggests is that it's easier to recall Chinese characters that include some kind of sound-based information because they provide a means with which to encode that information into short-term memory more easily than something that is just visual alone, right? So again, that very strongly suggests that information that's successfully encoded or transferred into short-term memory has some kind of sound property to it, right? Which makes sense because when we think about maintenance rehearsal as being the control process that allows us to keep information in short-term memory, right? It would be very hard to rehearse something that doesn't have a phonological component to it or sound-based component to it. Okay, so we've talked about the capacity of short-term memory, or how many units of information can be stored in short-term memory. We've also talked about the nature of information that gets stored in short-term memory, or how information is coded in short-term memory. So the last thing we're going to talk about with respect to short-term memory is duration, or how long information stays in short-term memory before it is forgotten. So basically, first I'm going to talk about the task that is used to determine, or was used by cognitive psychologists to determine how long short-term memory lasts. So this is called the Brown-Peterson task, and you guys actually completed this task on your own for yourself in your lab assignment for this week. So with the Brown-Peterson task, first you see what's called a trigram, which is again just a string of 3 letters. So in this case we have CHJ, and then you see a number, and your instructions are to count back from that number by 3s for a set period of time, right? So in this case we have 506, so you would count back, okay, 506, 503, 500, and so on. And so basically after that set period of time, you would be asked to recall the trigram, or the series of letters that you just saw. And basically the point of the counting back task is to prevent rehearsal, or prevent maintenance rehearsal, right? Because maintenance rehearsal is the thing that allows you to maintain information in short-term memory indefinitely. So if we're trying to figure out how long information can last in short-term memory without intervention, then we would want to stop that rehearsal process. So these are the results of Peterson and Brown. They both conducted experiments that were very, very similar, so we often look at both of them. So what they found is that when they collapsed across all their trials, right? So when they looked at multiple iterations of seeing a trigram, counting back, recalling, seeing a trigram, counting back, recalling, what they found is that on average, after 3 seconds of counting back by 3s, participants were able to recall about 80% of the trigrams, whereas at about 18 seconds of counting, participants performed at about 10%. So looking at that collective data, what Brown and Peterson concluded was that what was happening was the same thing that happens with sensory memory, right? As time goes on, there's a decay process, or a process in which information is forgotten solely due to the passage of time, right? So they reasoned that after delays of about 18 seconds, the information is forgotten simply because of the passage of time, right? But there's another explanation, right? So you guys might be familiar with the idea of interference. So interference simply means forgetting or a lack of access to something in memory because the information that you're trying to recall has been displaced by other information. Right? So when we talk about interference, again, we mean displacement of some information in memory by other information. Okay? And we can distinguish between 2 types of interference. So we have proactive interference and retroactive interference. So you guys might not know this, those of you who haven't met me, but my area of expertise as a cognitive psychologist is in the area of memory. So this is the sort of general topic of my research, my own research, is human learning and memory. And I know things about memory due to the scientific experiments I've conducted, but I also remember things that were difficult for me to learn as an undergraduate. And proactive and retroactive interference is one of those concepts that's very, very tricky to learn because their definitions are very, very similar, and it's easy to mix them up. So what I would advise you to do if you're trying to learn these concepts for the first time is do not memorize or attempt to memorize the definitions because you will mix them up. So what I would suggest you do instead is memorize or remember examples of each type, and then use the examples to get a definition. Okay, so we'll go through each type and I'll give you multiple examples to help you learn and hopefully remember these concepts. Okay, so proactive interference is going to occur when information that was learned previously interferes with or makes it more difficult to learn new information. Okay, so one example is language learning. Your native language may make it more difficult to learn and remember a new foreign language, right? So obviously your native language was learned first or learned previously prior to your attempt to learn a new language, and therefore that native language is going to displace or block out or occlude new language information. Another example, and this is one of my very favorite examples, comes from a friend of mine who is also a memory scientist, interestingly enough. And this happened to him personally, which is why the example is so funny. So another example of proactive interference is calling your current significant other by your previous significant other's name. Okay, so yet another example of prior information, right? If you have a lot of ex-girlfriends or ex-boyfriends, right, their names are going to be more prominent in your memory than those you don't know as well, right? So calling your current significant other by previous significant other's names would be another example of proactive interference. And retroactive interference is really the same concept except the inverse. So retroactive interference is going to occur when new learning makes it difficult for you to remember previously acquired information. So new learning interferes with remembering old learning. So one example of this might be you get a new telephone number and use it for a while, and you might have difficulty remembering your old phone number, right? Same with address. If you've lived at a new address for a long time, you might forget your previous address. Another example, for many of you, when you first started college, maybe you had the opportunity to purchase a brand new laptop, right? So maybe you got a MacBook Pro with a brand new iOS, or you got a Surface Pro with the latest version of Windows, right? And then you got that computer in August, and then when you went home in November for your first break with your family, maybe you forgot your new computer, and so you were forced to use your parents' computer, and your parents have a Compaq or a Dell computer that's running Windows Vista or Windows XP, right? So maybe you were used to using that old clunky computer before you went off to college, but now you have a lot of experience using this new computer, and so it's harder for you to remember the old program, right? One final example is if you have a new iPhone, right? The iPhone 10R and beyond no longer have a home button that you click, right? So if you spent a lot of time using your current device, right? Then maybe when your friend who has an iPhone 8 hands you their phone, and you have to use a home button, it seems odd, or you have difficulty doing it, right? Okay, so all of those are examples of different types of interference. Okay, so what does all of this have to do with the duration of short-term memory, or how long information can persist in short-term memory? Well, let's go back to the original Brown-Peterson results, right? So like I told you, when they looked at all of the trials together, right? So when they looked at all of those cases where participants saw 3 letters, counted backwards by 3 at various delays, and then recalled what the 3 letters were to the best of their ability, what they found is that there was a really dramatic difference between whether you had a delay of 3 seconds of counting or a delay of 18 seconds of counting. And what they found is that you had 80% recall in the 3-second delay versus 10% rate of recall with 18 seconds of counting. So that's a 70% difference depending upon the delay, right? So what that suggested to Brown and Peterson was that what was happening is that with the passage of time, information in short-term memory was rapidly forgotten, and it was only the passage of time, right? There were no other factors at work. But interestingly, other researchers, Keppel and Underwood, in 1962 decided to look at the same data, but they broke it down a little bit differently. So instead of looking at the average performance across many trials like Peterson and Brown did, they chose to look at individual trials. And interestingly, when they looked at the first trial, so the first instance in which participants saw a trigram, then saw a number and counted back by 3s for a set amount of time, what they found is that there was virtually no difference in recall between participants who counted by 3s for 3 seconds versus participants who counted backward by 3 for 18 seconds, right? And that really does go against Peterson and Brown's conclusion, right? That it was simply the passage of time that was causing forgetting of this information, right? Because if what matters is the number of seconds, right, of delay, right, then we should see the same dramatic difference in recall or the drop in memory performance on the first trial that we saw when all of the trials were averaged together, but we simply don't see that, right? But interestingly, when they looked at the third trial, or the third instance in which participants looked at the trigrams, counted back, and then tried to recall the trigram, they found that there was suddenly a difference emerging. So suddenly, people with a delay of 18 seconds were recalling fewer of the trigrams than people who counted backwards for 3 seconds, right? So how did they explain this? Well, the fact that there was little decrease in performance on trial 1 and more of a decrease by trial 3 seems to be consistent with the notion that there was proactive interference going on, or that previous trials were interfering with later trials, right? So having previously learned a number of trigrams, right? Those previously learned trigrams were making it much harder for people to learn the more recent trigrams, right? So certainly there was some effect of delay if we look at the difference between 3 seconds and 18 seconds on the third trial, and there is a slight difference between 3 seconds and 18 seconds even on the first trial. But by far, what seems to be causing the forgetting is not delay alone, but proactive interference. Okay? All right, so that concludes our discussion of short-term memory. And so my next video is going to focus on a concept called working memory. All right, so I'll see you guys in my next video.